Welcome, everyone, to today's Explainer. Listen, I am so incredibly thrilled you're here because today we are going to completely dismantle a massive, widely believed myth in the system design world. Seriously, if you've spent any time reading system design books or prepping for tech interviews, you've almost certainly encountered some very rigid rules about databases. Well, today we're specifically targeting the enormous misconceptions surrounding MongoDB and ACID compliance. So get ready to update your mental models because what we're going to cover is going to change exactly how you look at database architecture. Okay, let's dive into this. Here is our roadmap for today. We'll hit the system design myth, ensuring atomicity with transactions, isolation versus race conditions, the truth about consistency, why durability is non-negotiable, and wrap up with the interview takeaway. You know the golden rule we've all been taught, right? SQL databases are strictly ACID compliant, while NoSQL databases only ensure base properties, meaning they're basically available, soft state, and eventually consistent. That's the accepted industry standard binary. It's clean, it's super easy to memorize, and honestly, it's highly misleading. We're going to break this misconception wide open. Section 1. The System Design Myth. Debunking the Database Divide. Here's the absolute truth that gets buried in simplified textbooks. Literally nothing structurally prevents a NoSQL database from being ACD compliant. To prove this, we just need to define our playing field. ACD stands for atomicity, consistency, isolation, and durability. These are the 4 pillars that guarantee reliable database transactions. For the rest of this explainer, we're going to tear down this acronym piece by piece and see exactly how these properties work in MongoDB. Let's move to Section 2, Ensuring Atomicity with Transactions, the all-or-nothing rule. So atomicity basically ensures that during a request, either all queries execute successfully or none of them do. To really grasp this, imagine you're building a ticket booking system. In real life, you have to run a sequence. First, you check if the ticket is actually available. Second, you mark that ticket as booked in the inventory. And third, you map the ticket to the user by creating a record in the bookings table. But wait, what if the server completely crashes right before executing that third query? Queries 1 and 2 executed perfectly, right? So the database knows the ticket is booked. But the server crashed before the system could record who actually booked it. This crash leaves the ticket unsold in your overall business inventory, but falsely marked as booked in the database system. That means no real user can ever buy it. It's a massive bug. This is exactly where atomicity saves the day. If we could somehow revert the partial execution of those first 2 queries, we'd guarantee our all-or-nothing rule. And the way we achieve this is through transactions. Transactions wrap this entire sequence of queries into a single session and log every single event to the disk. Because these logs are saved physically, they persist even if the entire database crashes. When it revives, it immediately reads these logs and seamlessly reverts any partially executed changes before it accepts any new queries. Now, here is where the myth totally falls apart. NoSQL databases don't enforce strict schemas, sure, but the lack of a strict schema has absolutely nothing to do with storing logs to revert partial changes. Just like typical SQL databases, MongoDB has a mechanism for this. It uses something called oplog. This is exactly similar to PostgreSQL's write-ahead log or MySQL's undo logs. In MongoDB, these transactions are known as MongoDB sessions, and through replica set configurations, they utilize the oplog to absolutely guarantee atomicity. The A in ACID is right there, built into the NoSQL engine. Let's move to Section 3, Isolation versus Race Conditions, Handling Concurrent Users. In the real world, you aren't building a system for just one user. You have thousands interacting simultaneously. Isolation is all about keeping things safe when it gets crowded. It ensures safety while executing concurrent units of work that are trying to manipulate a shared resource. Basically, it makes sure simultaneous requests don't crash into each other. And this brilliantly illustrates what happens when you don't have isolation. Picture Alice and Bob. They both want the exact same ticket, and they click buy at the exact same millisecond. Alice's request checks the ticket, it's available. Bob's request checks it a microsecond later, also available. They both update the status to booked, and the system creates a booking record for both of them. This is a classic race condition resulting in 2 people showing up for 1 seat. A total nightmare. Race conditions are a generic problem, which means they have generic solutions. There are primarily 2 ways to fix this: lock and snapshot. With a lock, when we read a data point, we literally lock it.
So if Alice is looking at the ticket, Bob's request has to wait in line until Alice's transaction is entirely finished and the lock is released. The second approach is a snapshot. Here, Alice and Bob read different versions or snapshots of the data. When they both try to commit their purchase at the very end, the database engine detects a conflict between the versions and simply aborts one of the attempts.
So how does our NoSQL contender handle this? Well, MongoDB provides snapshot-level isolation between sessions by default. It inherently prevents these race conditions. By utilizing snapshotting, MongoDB ensures that inconsistencies caused by multiple users hitting the same shared resource simply do not happen. Boom. That's the I in ACID firmly established in MongoDB.
Section 4. The truth about consistency. Dispelling the eventually consistent rumor.
Now, I can practically hear you thinking, wait a second, isn't NoSQL eventually consistent? It's one of the most stubborn rumors in system design. People always point to horizontal scaling and cluster solutions for replication. But here's the reality check on horizontal scaling. Temporary inconsistency from replica lag happens in NoSQL, yes, but it also happens in SQL databases like PostgreSQL when you're using read and write replicas. The delay is a product of distributed architecture. It's not a flaw in the database paradigm itself. Because MongoDB supports the atomic, isolated sessions we just talked about, it absolutely ensures the strong consistency you'd expect in a typical SQL database. When a transaction commits in MongoDB, the data moves from one valid, consistent state to another valid, consistent state, period. That is the C in ACID.
Moving on to Section 5, durability is non-negotiable, saving your data permanently.
I want you to really think about this for a second. Can we actually even call something a database if it stores data in a volatile fashion and loses everything the second someone unplugs the server? No, of course not. That's just in-memory caching at best. So the crucial point is that because we call MongoDB a database, it inherently stores data in a non-volatile, durable fashion. It writes to disk, it saves your data permanently so it survives power losses and system crashes. And with that D for durability, we have successfully proven that MongoDB is atomic, consistent, isolated, and durable. The whole ACID teardown is officially complete. Finally, Section 6, the interview takeaway, a final piece of advice. So why does mastering this granular distinction actually matter? Because in your next architecture review or system design interview, stating outdated myths is going to undermine your credibility. I want to leave you with a direct quote from our source material. I hope now, when you will be asked in any interview, what is the difference between SQL and NoSQL, please do not end up saying we need SQL for transactions. Be the candidate who actually explains how MongoDB uses oplog and snapshot isolation to achieve ACID compliance. If NoSQL can be ACID compliant, what other fundamental system design rules might just be flexible design choices? Keep questioning those defaults, guys, and keep learning.